Good morning, friends. Today we should be dealing with theories of failures. Myself, Dr. Kushal Bhattacharya, and I today discuss about the theories of failure which normally occur for a mechanical components. Now, in mechanical components, in specimen level, there could be a sharp yield point, ultimate point, fracture point, but that is for the specimen level. When we are going for a component level, that understanding varies a lot because there are certain mechanical components. There can be more than one, two, or three types of forces. That is, biaxial, triaxial forces are acting simultaneously on the component. So that theory, so there you, in normal cases, for in the specimen level, when you are performing an experiment, there are only a single type of load is acting. But when you are going for studying the same components in a same component made up of the same material, there are several types of loads are acting on it in simultaneously. There can be torsion, there can be bending, so there can be axial, there can be axial load with torsion, compressive load with torsion. So there there is no sharp design criteria for a component which is subjected to biaxial or triaxial loading. For that reason, there are several theories of failure which suggest different ways by which you could think a failure could occur. There are several scientists who propose different theories by which you could suspect a failure mechanism which is taking place in a component level. So basically, if you see that there are several types of failure which are occurring simultaneously to a mechanical components. For example, if we take a power screw, we could see that there is a torsional force along with axial force applied. So the component which is made up of power screw can have a separate yield point or yielding point, ultimate point, but when you are making the component, you cannot design on the basis of the yield point because there are two loads are acting. There is torsional load and axial load. Again, when you go for a overhanging, when you are going for overhanging crank also, there is a combined bending load along with the torsional load. So in a overhanging crank, you could see not a single load. Here one is bending load is acting and another is torsional load is acting. Similarly, bolts or brackets are subjected to tensile forces and shear forces. In that condition, there you could not judge the material by a single yield point or ultimate point. For that reason, the failures are broadly classified into two types. One is the elastic failure and another one is yielding and fracture. Now, elastic failure, what happens, results in excessive elastic deformation of a mechanical component which make it unfit for use. So elastic failure, that means the system is the component, not the specimen. The component is deformed by the action of two or three different types of loads, and it is deformed in such a manner that it becomes elastically deformed in such a manner that the normal working of it is rendered or hampered. So that is one sort of failure. Another sort of failure is called yielding or fracture. Now, in yielding or fracture results in plastic deformation. It occurs an excessive plastic deformation after yielding. So this is also considered a second criteria of failure, yielding, which is called as the yielding and fracture. Now, we will basically concentrate our theories of failure studies based on this elastic failure. Now, I told you that there are several scientists thought because it is a component level, there can be a mixed mode of failure. By action, that there can be the loads are applied, that is in torsion and tensile. So in compression and tensile. So different scientists thought that the failure could be different. The failure mechanism, there everyone's perspective of thinking is different. So first, one of the theory is proposed, which we should be studying, is called the maximum principal stress theory, which is normally also called maximum normal stress theory. Maximum normal stress theory. So this is the first theories of failure, which is called the maximum principal stress theory or the maximum normal stress theory. It is proposed by W.J.M. Rankine in the year of 1850. So it is also called the Rankine's theory of failure. According to this theory, it suggests that the failure of a mechanical component subjected to biaxial or triaxial stress occurs when the maximum principal stress exceeds the yield point stress for that material or for that material. So, example, a material is made up of a component is made up of some material. So you perform a tensile test of the same material and you get a yield point, ultimate point. But when you are studying on the component level, there can be a biaxial stress or triaxial stress. But Rankine states that failure in the component level or failure in the component can occur when the maximum principal stress exceeds the yield stress or the ultimate stress of the material. Then failure of that component occurs. For example, if a component is made up of a material, this sort of material, so it can be subjected by a compressive stress and shear stress. So it is a case of a biaxial force. Now I have just cleared this portion and I'm explaining it. So for example, if a component is subjected to biaxial force, that is tensile force along with torsional force, So this is the case of a biaxial force. If we give a bending to it, if we give another force, then should be triaxial force, bending force. Now the thing is that if a component is subjected to if this is a component basically subjected to a biaxial or triaxial stress, so as I've discussed, failure will occur according to Rankine if the material of the component is ductile. So we should follow the ductile stress strain curve. This is the ductile stress strain curve. There is a sharply defined yield point, no problem for that. So if there are three principal stresses acting, sigma 1, sigma 2 and sigma 3, and if sigma 1 is greater than the maximum principal stress, so if the maximum principal stress is equals to the yield stress in tension, then what happens? Then fracture will take place according to Rankine. If the material is made up of a brittle material, what happens? If the material is a brittle material, what will happen? There is no sharply defined yield point and fracture will take place. So this is the ultimate stress. So if the material is made up of brittle material, if the component is made up of brittle material, then the criteria, the maximum principal stress, if it is equals to the ultimate tensile stress of the material, then fracture will take place. So if we put the factor of safety over here, we will get sigma ys by factor of safety, or sigma 1 is equals to sigma ys by factor of safety. We should get this criteria. According to this criteria, this is the formulation. Now if it is subject to a compressive force, what will happen? If it is subjected by a compressive biaxial force, then what happened? Then same thing, maximum principal stress, if it becomes to equals to sigma yield stress, if it is for tension, and this is for compression. If it is for ductile material, should be the criteria. And if it is for the component is brittle material and in compression, the criteria should be sigma ys compression, there should be sigma us ultimate stress. So sigma us compression by factor of safety. This is us. This is US. So sigma US by factor of safety. So for the thing is that when it is in tension, when it is tension, it will follow this criteria, and when it is compression, it will follow this criteria. Sigma y is compression by factor of safety, or sigma maximum principal stress is equals to sigma ys compression by factor of safety. So ultimately we say that if sigma 1 is greater than the if the material is made of ductile material, for tension sigma 1 should be equals to sigma by maximum principal stress should be equals to the yield stress by factor of safety, and if the material is made of a brittle material, then sigma 1 should be equals to sigma 1 by US ultimate stress by factor of safety, where there is no defined yield point. For compression, this will change for tension loading, and for compressive loading, if you see the for compression loading, the sign will only change, nothing will differ. The sign will only change if it is for brittle material, and if it is for ductile material, it should change like this. It will change like this. So basically, this for compressions, and for if the material is made up of ductile, and for if this component is made up of for tension, it is then this should be sigma ys. So this is the condition. Now, according to this theory, the region of safety, if you want to plot the region of safety for a component subjected to biaxial loading, so this is the required plot for a component subjected to biaxial loading, with the assumption that what we have assumed is that sigma yield point is equals to sigma yt yield point tension, sigma yield point, sigma yp tension is equals to sigma y compression. Sigma y tension is equals to sigma y compression. This assumption we have assumed. So what should be the yielding point for in tension? The same should be the yielding point for in compression. This we have assumed. Based on this, we have taken that the x-axis represent the sigma 1 principal stress. So there are two principal stress, as we have taken biaxial loading, there is sigma 1 and another one is sigma 2. So along the x-axis we have plotted the value of sigma 1, and along the y-axis we have plotted the value of sigma 2. So you see that in this region this is sigma 1, and this is minus sigma 1. So this one is tension for sigma 1, and this portion is compression for sigma 1. Similarly, in the y-axis, this portion is tension for sigma 2, and for the y-axis minus sigma 2 represents the compression. So any component, if sigma 1 2, if the coordinate of this value of sigma 1 2 in any permutation or combination, if it lies within this region, then the material can be considered, then the component can be considered, failure will not take place. Suppose if the coordinate comes over here, so it could be assumed that the failure will not take place. If the component that is sigma 1 is also in tension and sigma 2 is also in tension and it lies in this region, so failure will not take place. If the point is over here, that is as if sigma 2 is in compression and sigma y is in tension. If the loading occurs in this coordinate, the failure will not occur. So it is same for over here also, here also. But if sigma 1 and 2 lies outside this component, so then what happens? Failure will take place. So if we consider this, so while designing a structure, we will always consider that this region we have to keep in mind in this region for a biaxial loading. So this ends of today's lecture of maximum principal stress theory of or the Rankine stress theory or the maximum normal stress theory. So we have first, if we jot down what are the things we have discussed. First we have discussed what should be the failure, what should be the requirement for designing of failure for in a component level. So we have and the different types of loading, that is biaxial loading or triaxial loading. So what happens, and we have studied the maximum normal stress theory or maximum principal stress theory or Rankin's theory. So this ends of all about the lecture. Thank you. Have a good day.